99% of paleontologists miss this crucial detail. These ancient structures tell stories of survival. Dinosaur teeth are the ultimate record of diet. Now that we understand their importance, let's explore types. Consider the massive jaws of the plant eaters. A herbivore teeth needed grinding power, not piercing strength. But these teeth were broad, designed for continuous wear. Many herbivores possessed dental batteries for replacement. This continuous renewal ensured lifelong processing of bulk food. Now that we understand grinding, let's pivot to tearing. Carnivore teeth feature xiphidonty, tiny steak knives on edges. But these serrations acted like bandsaws during the bite. The iconic apex predator possessed these specialized instruments. The depth and curve dictated the amount of tissue damage. Unlike herbivores, these teeth were often replaced slowly. But some meat eaters needed crushing force, not just slicing. And these osteophages utilized robust, conical teeth for bone destruction. But comparing slice versus crush reveals distinct feeding niches. Now that we understand pure diets, let's consider flexibility. Omnivorous dinosaurs evolved generalized dental wear patterns. This allowed opportunistic feeding across plant and animal matter. Their survival hinged on maximizing resource utilization efficiently. Some specialized groups developed unique adaptations for slippery prey. But piscivores often had long, thin, recurved, pointed teeth. But these acted like efficient fish hooks, preventing escape. Notice the lack of grinding surfaces in these specialized jaws. But let's now consider the surprising case of armored dinosaurs. Their teeth were small, often leaf-shaped, yet highly effective. Jaw mechanics, not massive size, delivered the necessary power. And they processed tough materials through sheer tooth density. And now that we understand diet, let's examine the material science. Dinosaur enamel structure varied significantly across species. A harder enamel resists immediate abrasion from gritty food. But wear facets tell paleontologists exactly what the animal ate. The whole dental arcade represents a unified functional unit. Bite force calculations often rely heavily on tooth robustness. And the shape distributes the incredible mechanical stress applied. A weak tooth indicates a weaker bite structure overall. But not all dinosaurs possessed true teeth in the traditional sense. Beaks were used for cropping, often supplemented by gastroliths. The stomach stones performed the grinding work internally, a different strategy. This contrast highlights the diversity of Mesozoic solutions. And now that we've categorized structure, let's look at discovery. A careful excavation preserves the context of these vital clues. But documenting the exact position is non-negotiable for science. Each tooth fragment adds a piece to the ecological puzzle. In the lab, advanced imaging reveals hidden information. We can virtually reconstruct the entire tooth replacement cycle. Lines within the dentin can even suggest growth rates. And these physical traits directly informed dinosaur behavior. A crushing bite meant conquering larger, thicker-skinned prey. Wide dental batteries enabled mass consumption of low-quality flora. But even the smallest dinosaurs had highly specialized dental requirements. Every tooth shape reflected a critical niche in the ecosystem. These dental adaptations evolved over vast stretches of deep time. And evolutionary pressures honed these instruments with relentless focus. The result is a biomaterial marvel, perfectly suited for its task. We are privileged to examine these remnants of ancient mechanics. But each serration, each facet, encodes the life of a giant. The story of the dinosaur is etched indelibly in their very bite.